We are going to talk about logarithmic functions. The definition of a logarithmic function, it's the inverse function of the exponential function. Okay? This is the logarithmic function. So the definition of a logarithmic function becomes y equals, or f of x equals, log base b of x is equivalent to b raised to the y is equal to x. X has to be greater than 0, and b is your base, so it has to be greater than 0 and not equal to 1. The logarithmic form, y equals log base b of x. Here's an example, log base 5 of x equals 2. The exponential form, b raised to the y equals x. So in that previous example, 5 to the second equals x. That's your exponential form. All right, let's do a couple examples where we're going to write the equation in its equivalent exponential form. So let's say number 1, we have log base 2 of 64 equals 6. All right, so this is nothing that we have to solve. This is actually a true statement. All we're doing is rewriting it. So the base of our log is the base of our exponent, so 2 to the 6th power equals 64. So 2 to the 6th equals 64. So we can see that that's just a true statement. All right, so another example, let's say I have log base 5 of 125 equals y. Fix that 5. And all I'm doing is rewriting it. Again, nothing to solve here. I'm just rewriting it. So the base of my log is the base of my exponent. So I have 5 to the y equals 125. 5 to the y equals 125. All right, now we're going to do a couple examples where we're writing the equation in its equivalent logarithmic form. So if I have, let's say 5 to the 4th equals 625. Now we're going to write it in its logarithmic form. So that means I need the word log. So I'm going to go ahead and write log base. Okay, the log's base is the same base as the exponent. So what is the base of my exponent here? 5 of 625 equals 4. So anytime you're looking for the log, it equals the exponent. So now another example. Let's say I have something like 2 to the negative 4 equals 1 divided by 16. So again, this is just a true statement. All I'm doing is rewriting it in its equivalent logarithmic form. So I'm going to start off by saying log base, the base of my exponent is 2, so 2 of 1 divided by 16 equals negative 4. So log base 2 of 1 divided by 16 equals negative 4. So the base of my log is 2, right? And it equals the exponent. One more example that we would look at would be 1, like the cubed root of 64 equals 4. Now with this one, right, I don't see an exponent, so I have to remember that when I have the index of 3, right, that's in the denominator of my exponent. And then my exponent underneath here, what's the exponent on 64 that I don't see? 1. So I can then turn around and write this as 64 to the 1/3 power equals 4. All right, so I'm just writing it in that form so that I see my exponent. I didn't move sides or anything like that. So now I'm going to go ahead and say log base. What's the base of my exponent? 64 of 4 equals 1/3. All right, now we're going to look at a couple examples of evaluating without using a calculator. Those are your directions. This is a mental math. Anytime you see the word log, you need to think, what is the exponent? So when I look at number 1, the first thing I say is log base 7 of 49. That's how you read it. But then as soon as you see it's asking you for the log, that means that it's asking you for the exponent. So you would say, what is the exponent on 7 that gives me 49? My answer here is 2. Number 2, log base 6 of 1 divided by 6. So what is my exponent on 6 that gives me 1 divided by 6? So what makes it a fraction? What gives me that reciprocal? A negative. And then 6 to what power is 6? 1. All right, let's look at number 3. Log base 3 of the square root of 3. So what is my exponent on 3 when I have the square root of 3? Remember, my exponent here is 1. My index is 2, so my exponent is then 1/2. 3 is not a perfect square. That's why we have the square root of 3. Now, the same thing is true for number 4, right? What is my exponent on 81 that gives me 9? Well, what do you have to do to 81? 81 is a perfect square. That perfect square is 9. So this is then 1/2. All right, then looking at number 5, right? It says, what is my exponent on 5 when I have 5 to the 7th power? 7. I bet you thought it was going to be something else. It's just 7. Here, this is inverse functions. When you take 7 as your base and you raise it to log base 7, you're talking about inverse functions. So when you have the inverse functions, they cancel each other out. So here my answer is just then 52. Here are your your properties. You have your general properties, your common log properties, and your natural log properties. Your general properties, log base b of 1 is equal to 0. That's because my exponent that get on my base b that gives me 1 is 0. Log base b of b equals 1. That's because b to the first equals b. Log base b of b to the x is equal to x, because this is asking for what is my exponent on b that gives me b to the x. It's just x. When I have the base b and I'm raising it to a log base b, then I'm doing an inverse function. So therefore b raised to the log base b of x is then just equal to x. Your common log properties, you'll see your common log properties are the same as your general properties. The difference here is if you don't see a base on your log, then the base is 10. Your natural log properties, remember that ln is the same thing as log base e. So ln is the same thing as log base e. These are your properties. They're the same properties in each section. All right, here's a couple more examples of evaluating without using a calculator with common logs and log base e, or ln. ln is the same thing as log base e. So this says here the common log of 100. So if I don't see a base, then I know the base is 10. So this says, what is my exponent on 10? That gives me 100. So my exponent is, of course, 2. Number 2 says the common log of 1 divided by 10,000. So this says, what is my exponent on 10? That gives me 1 divided by 10,000. So I have that 1, so I know my exponent is negative. And then I have 1, 2, 3, 4 zeros. That's the easiest way to see what your exponent is on 10, is to count your zeros. All right, number 3, ln of e says, what is my exponent on e when I have e to the first power? So my answer here is just 1. Looking at number 4, what is my exponent on e when I have 1 divided by e to the 8th? So therefore I know I have that 1, so I know my exponent is negative. And then what is my exponent on e? 8. And then of course ln of 1, that means what is my exponent on e that gives me 1? Anything to the 0 power gives you 1. The graphs of exponential and logarithmic functions. So remember that they are inverse functions. So that way when we look at this, we can see this one, this pink one right here, is our f of x is equal to 5 to the x power. That's your exponential function. That's from 4.1. Your inverse of that, f of x is equal to log base 5 of x. This is your log function now. They are inverse functions of each other. You can see because they reflect over y equals x. So now anytime you see a log graph, your log graph looks like this. The properties of your logarithmic function graphs. So here it has log base a of x. Your x-intercept is the point 1, 0. That's because, remember, your x's and y's change places. If a is greater than 1, then the graph is increasing on its domain. If a is between 0 and 1, then the graph is decreasing on its domain. If there is no base, assume 10. The y-axis is now your vertical asymptote. The domain is from 0 to infinity, where your 0 is not included, and the range is from negative infinity to positive infinity. So just kind of looking at the graph again, this right here, whoops, is your log base graph. That really shouldn't be touching there, but we'll just go with it. So that's what your graph is going to look like. Now you have a vertical asymptote at x equals 0. Notice your domain. There are no negatives here. Your natural logarithm is the logarithm to base e, where e is your irrational constant, approximately equal to 2.718281828, and keeps going, right? Because it's irrational. The natural logarithm is generally written as ln of x, but it's the same thing as log base e. Sometimes you'll want to use log base e, but you have to remember that ln is the same thing as log base e. The natural log gives you the time needed to reach a certain level of growth. So in other words, if e to the x is the amount of continuous growth after a certain amount of time, right, you're plugging in x, the natural log of ln is the amount of time needed to reach a certain level of continuous growth. Here's again an example of your exponential growth graph, right? So here's your natural base graph. Here's your ln graph. How to find your domain. If you have f of x is equal to some logarithmic function, this is ln of something, you set whatever is in the parentheses greater than 0, because your domain has to be greater than 0. But with our transformations, do we see that our domain can change based on a transformation? Absolutely. It's whatever is happening to the x. Whatever is in parentheses, you set it greater than 0. Solve the inequality. All right, so here are examples of finding the domain of each logarithmic function. Here I have f of x is equal to log base 5 of x plus 6. That x plus 6 is in my parentheses, so we just saw whatever is in the parentheses, x plus 6, you set it greater than 0. And solving here, so therefore I subtract 6 from both sides, so I get x is greater than negative 6. So therefore my domain is from negative 6, which is not included, to infinity. On our next example, we have our f of x is equal to the common log of 7 minus x. So just like before, whatever is inside the parentheses, you set it greater than 0 and solve. So here, the first thing I'm going to do here is subtract 7 from both sides. So now I have negative x is greater than negative 7. Then divide both sides by negative 1. What happens then when you divide by a negative 1? You have to flip your symbol. So therefore my domain is then my lowest possible value, negative infinity to 7, where 7 is not included.